Good morning, good afternoon, good evening to all our friends from around the world. Welcome back to the inaugural symposia of the American Express Lab for Data Analytics, Risk and Technology. It's my pleasure to invite you back. We had one inaugural lecture yesterday, and we have a series of 3 lectures today. We have Professor Katsikopoulos from the Institute of Southampton, followed by Dr. Manish Gupta from American Express, and Professor Narayanan Srinivasan from IIT Kanpur as the 3 speakers today. To chair the first session, I invite Professor Ravindran, who is a professor in the Department of Computer Science at IIT Madras. He is also a Maitri Faculty Fellow and also the head of the Robert Bosch Center for Data what is it? Data sciences and AI. And so over to you, Ravi.
Thank you, Raj. And you forgot to mention I'm also a core member of GARD. So.
Absolutely.
Okay. And it's a great pleasure to be introducing Professor Konstantinos Katsikopoulos. So co-stars, as we know him, and I were actually there at UMass at the same time. So Konstantinos is a tenured associate professor and head of research at the Department of Decision Analytics and Risk at the University of Southampton Business School. Previously, he was an associate professor and deputy director of the ABC group at the Max Planck Institute for Human Development, as well as visiting assistant professor at MIT and the Naval Postgraduate School. He works on integrating standard decision theory with the simple rules of thumb that people actually use. He is engaged with government and businesses on complex problems in economics and safety. His work has been funded by organizations such as NASA Ames Research Center and the German Science Foundation, and covered by newspapers and magazines, such as Science News. He was one of the 2 speakers in the first plenary debate at the OR Society meeting on optimizing versus satisficing. Konstantinos is a co-founder and organizer of the annual Winter School on Bounded Rationality in India at the TAPI Management Institute, chair of the OR Society's Behavioral OR Group, and serves on the editorial board of Judgment and Decision Making at Journal of Mathematical Psychology. He's the lead author of Classification in the Wild, The Science and Art of Transparent Decision Making, forthcoming by Mighty Press. Konstantinos, over to you.
Great. Thank you very much, Ravi. Let me see if I can share my content. No. See it? Yes?
Yes.
I'm guessing. Okay, great. So it's great to be here. I'm very glad to be participating in the inauguration of the DART Lab. Very excited about the mix of analytics and behavioral science that you're trying to pursue. I think this interdisciplinary approach is absolutely the way to go for such hard problems. Since we don't have so much time, I'm going to get immediately into my talk, and then I'll be making some connections. As Ravi said, I know a few of you, of course. Ravi also, Narayanan, he was participating and gave us some nice lectures in cognitive psychology in the summer schools for bounded rationality we're holding at TAPMI every year. And of course, Nandan, with whom we overlapped at MIT and at the Max Planck. So I'm going to present an outline of a book project that we initiated 3 years ago. It has exactly the title that you see in the screen, and as Ravi said, these are co-authors, and indeed, actually, as Ravi said, the person on the left, Ozgur Simsek, she was a fellow student of Ravi in the machine learning lab at UMass Summers, headed by Andy Barto. That's Ozgur Simsek. She's also my wife. Her student, doctoral student Marcus Bookman, is a senior data scientist at the Bank of England. And on the right is Gerd Gigerenzer, who is our mentor in that kind of work. And I would say a very influential person into carrying over Herbert Simon's work. Herbert Simon, possibly one of the most important polymaths of the 20th century in the intersection of pretty much the kind of thing Dart seems to want to do. So building mathematical models, formal models for decisions in the real world, but respecting the information processing of people and by extension of machines, hence making them more usable and transparent. So in a way, I already gave you a little bit of a background of what we try to do in that book project. This is the first scholarly book by the ABC group that puts together formal work, and it's not an edited book or a handbook. So it's a shorter book, and it's a book where we try to show to people how to do stuff and evaluate them and make a connection to cognitive psychology and machine learning. You will see. But before I get to, let's say, an illustration of some of the contents of what we did in order to bring together a few decades' work, let me do a little bit of preparatory work in terms of some definitions. So that will be the next 5 or 6 slides. Let me first say a little bit about this in the wild. I don't know if you heard it. It actually resonates well with the talk and the work that Greg Jamieson from Toronto was discussing yesterday. It's a classic thing in cognitive science, cognitive engineering, but not always so much followed or so much known in other disciplines. So in the lab is meant to be, let's say, an antonym to in the wild is meant to be an antonym to in the lab. So everything that approximates better the conditions under which real people and real machines have to make decisions and reason in the world as we experience it is in the wild and not in the lab where the experimenter or the modeler is trying to keep control in order to learn some things or run a control experiment and so on and so forth. I have an example here, and the example is has to do with a very English concern. So this is Bertrand Russell, of course. And the question is basically, should I go for a picnic tomorrow or not? Because it could rain. So in England, it could rain anytime. Even if it's brilliant weather, it could start raining. So that's how it works. So why am I putting that here? Of course, we all know that the world is uncertain, but we're also not that defenseless against this uncertainty. Of course, we have developed formalisms and have been refining them for hundreds of years, such as probability. That's our main device for reducing uncertainty into something manageable that we can apply calculus to. So if you consider the probability of rain, of course, we have those now. Your smartphone can give you one on an hour-by-hour basis. So we have managed seemingly to somehow reduce uncertainty into probability. Nevertheless, there's many subtleties. First of all, these probabilities keep changing. So it's a very unstable device. So your cell phone may say now that at 4 p.m. the probability of rain is 30%, but that can become 40%. Second, it's not clear at all what this 30% and 40% mean. There's many interpretations, frequently single event, and people are hopelessly confused about these interpretations. And third, and perhaps more damagingly, and now I'm moving here to Jim Savage, who was the founder of what is broadly understood or discussed to be Bayesian subjective expected utility theory. Even Savage himself said that his theory, applying probabilistic reasoning and probabilistic calculus to planning a picnic, it actually cannot be done. The problem is too complicated, even planning a picnic. So some of the problems are one cannot imagine all the possible events, one cannot attach probabilities to them, one cannot attach utilities to them, and so on and so forth. So in theory, Savage provided the solution, but then he himself said he thought the problem of planning a picnic is in fact too wild, it's too much in the wild. So the ABC group and another number of groups that interface with us, including Nandan's group at MIT, headed by Adam Fry, we have always been trying to make do with less information, possibly in the absence of probabilistic information, which is often the case in the wild. And you'll see that this tends leading you to simpler models that are less information hungry. And the question is, are these models able to perform as well as the more complex models? And I'll get to that. Beyond that, before that, the second preparation, I'm still in the preparatory phase, if you remember. So except for the wild, I want to explain will be transparency. So by transparency, of course, it's very close to the pronounced goal of AI these days, which is sometimes called explicable, interpretable, and so on and so forth. But transparency, we specifically define it as saying something that people, these are the agents in this case, can understand, can apply, can teach to others. And I want to show it a little bit by example, and this is in a way my first case study. So this is a real data set that we're using in the book. It has to do with Pima Indian older women in the United States. They do have a high prevalence of diabetes, about 50%. Can we predict, based on some attributes, cues, features, depending on our discipline, who of these women will develop cancer, diabetes within the next 5 years? Here in this slide, you see some solutions that exist already, and they're meant to be transparent. So I am constraining myself now in terms of AI models, in those models that are trying to be transparent. So for example, Leo Breiman's classification and regression trees are one such possibility, and random forest is, as you know, a collection of all these cart trees altogether. And you also have decision lists. So these three are AI's attempts, not the only attempt, but typical attempt of trying to be more transparent to people. And I'm going to be a little bit picky from the perspective of a behavioral cognitive scientist. So something I could complain about, if you look at the card, of course, it has a nice graphical structure. It asks questions. Everything that Leo Breiman was going for is here, of course. But there's some other things that can be disconcerting. For example, you have a question here, which is about the body mass index. And you see that if it's large, so if it's larger than 29.95, then you would predict diabetes for this specific person. That's fine. What could be confusing to someone who's not a data scientist is that a question on BMI comes up again with another value. And now, if you have a relatively large value, so larger than 26.35, you're not going to conclude as you did here before diabetes, but you're going to ask another question. So if you don't understand where this is coming from and that there is some kind of simple logical expressions that are different in this case, you may well be very again. It stand clearly, right? This is one complaint here could be more one the kind of we
Sir, you are losing your voice, sir. Hello? Professor, we are, there's a break in your voice.
I can do. Hello?
Professor, please kindly repeat that slide, Professor. Your video is frozen and there's a break in the net connection for you.
Your voice is breaking up.
So from that, now
So, your voice is still breaking up.
take any. How about now?
We can hear you now, Kostas.
Much better, yeah.
Yeah, well.
Kostas, one suggestion, maybe you can keep your video turned off. That might save some bandwidth, and just share the screen.
Yeah, let me do that. Okay, so a bit confused with all these windows now. How do I get to the? Oops.
We are still seeing your screen.
Yeah, I know, but
you just need to start your slideshow.
yeah, but you can also see the video, I think, which I was trying to.
I can see the video.
Yeah.
So all the way at the bottom of your screen, you should see a button with the video crossed out.
Could it be that if you're sharing, you cannot do this?
No. This should be like a floating panel that just shows up when you bring your mouse down, like that.
So as long as the mouse comes down, the panel will
Video options. Don't see anything actually. You can see my screen, right? So you cannot see that screen.
No, we can only see your PowerPoint.
Professor, you can stop sharing and again start.
Yeah, exactly. I think that will work. Stop my video. Now I'm sure it will work now. Okay, let's try again. Well, sorry about. Let's see now. So now, can you at least hear me, even if you cannot see me?
Yes, we can hear you clearly.
Okay, maybe that will help. So, is it true that people couldn't really follow the slides? Should I start from the beginning?
Preferably yes, Professor, because at the beginning we lost many of your words.
At the beginning, there started being problems. Okay, let's see how it goes this time. Okay, so what I was saying is for the prediction of whether a particular PIMA woman will develop diabetes in the next 5 years. AI, of course, has done some attempts to build transparent models, and those are either trees, as you see here, the CART tree by Leo Breiman, classification and regression trees, random forest, which is a collection of such unpruned trees, and decision lists, which are a series of logical expressions. So I'm going to be a little bit picky now and criticize why these things are not necessarily that transparent to non-data scientists. For example, if you take the card, there's a question here about BMI, body mass index. And what happens is if the BMI is relatively large, larger than 29.95, in that case, you predict diabetes. On the other hand, this question is repeated with another threshold value, 26.35. And now, in the case of a yes answer, you don't immediately conclude diabetes, but you ask another question. So you could try to get into the point of view of a person who's not a data scientist. They could be confused why you're asking them the question on the same cue twice, why you're not asking exactly the same question, and why you're performing different actions for the same answer. For the decision list, a complaint could be that sometimes, in order to be able to understand and what the algorithm is doing, why sometimes some questions include more than one cues, as for example is here with the plasma and the BMI. So in the kinds of methods we have been developing, which is the fast and frugal tree and tallying, as two examples, there are more, we don't necessarily change too much, but we're trying to make the structure more constrained and easier to follow for someone who thinks a little more simply and doesn't have the training of a data scientist. So in a fast and frugal tree, we do have a tree, but every time we ask a question, there's always the possibility that the classification is made, as for example, for the first, the second, for all the questions, as you can see. This is a constraint. All fast and frugal trees do like that. That's why they're frugal. They don't use much information, and hence they can also be quite fast. Now, another thing that we do in the fast and frugal tree, we also force that there are no questions that involve more than one cue. Okay, for the tallying also, we simply tally the reasons. This is similar to the decision list. but again, we don't allow for two cues to be asked in the same question. So these ideas come from first observing human behavior and noticing that people spontaneously use such methods to make their decisions. If they use something like the tree, they're more likely to use a fast and frugal tree. And if they use something like a linear model, of which tiling is a very special case, with the weights all being equal to 1, then they tend to use a tiling rule. Hence, the idea is that those things could be more transparent to real people, not only in the mind of data scientists. Of course, now you may say, yes, you made them simpler, fine, I can accept that. You made them more transparent, possibly. We need the empirical work for that. We have some, but not necessarily large scale. But you probably also made them less accurate. So I'm going to spend considerable time in this talk discussing that, but here's a first indication. For the problem we just saw, predicting diabetes in PIMA older women, you have the five methods here, and you have different measures. Balanced error, we just average the error due to misses and to false alarms, because they could be imbalance in the frequency of the classes. And then frugality, that we operationalize by the number of questions that are used for every classification, and transparency by the number of questions that are in every tree. Notice that those two are not exactly the same, because in some cases you stop before you reach the end of the tree or the end of the tiling rule, for example. I don't want to get too much into that, especially since we lost some time. But let me, you can quickly scan it, and you see there is a little bit of a trade-off, but maybe not as much as one thought. True, the random forest was better, but tiling was actually better than Reaper and as good as Cart. And clearly, as one may expect, the transparency, there's just simply no comparison between the fast and frugal tree scores and the scores of the other methods. Tiling is actually not so frugal because it always tends to use all of the cues. Okay, so this could mean that someone will have a reason to investigate this trade-off. It's not a given that if you make a model more transparent, you also make it less accurate. This is an empirical question. Okay, before in fact I get into this empirics and a little bit of a theory we have been developing about explaining the findings, let me quickly address something that could be in your mind. So if you have studied behavioral science and engaged in it, you have probably heard about other kinds of heuristics beyond this tiling and fast and frugal trees, and you may be curious how they relate. First, in terms of the definition of heuristics in operational research, their heuristics in computer science, this is from an operational research textbook, their heuristics don't really have to do much with people. People are consuming them as decision makers passively, but they're not producing them. So heuristics are simple computational shortcuts that allow to find a feasible solution. That's also a good thing. You don't always go for an optimal solution. In some problems, just finding a feasible solution is good. So that was a little bit of one of the original meanings of heuristics. And in behavioral science, Tversky and Kahneman have been extremely influential into proposing another meaning, which brings, of course, the people in the forefront. The people are now the producers of heuristics. And where before heuristic was associated with the word good, so to say, now it's associated passively with the word of error, as you see in this definition. Of course, Tversky and Kahneman were careful and they said sometimes heuristics are good, sometimes heuristics are bad. But the writing was such, as in this definition, that emphasized the errors. The definition that we are using in this work, and I would like somehow to put on the table, I think it's rapidly gaining ground in behavioral science and sometimes even more outside behavioral science, in more practical disciplines, is that heuristics, of course, are models of what people do. They are quantitative. They're not verbal labels as in the Tversky and Kahneman work most of the time, or at least in their original work. They're models, so possibly more amenable to formal analysis as we do here. And part of this definition also includes an attempt to say that sometimes they lead to good outcomes and sometimes they lead to worse outcomes. So before getting a little bit more into the meat of what we did, I wanted to place it in the broader context of behavioral science. I think that's important. As the DART lab is trying to make contributions that spawn and interact productively with other areas such as behavioral economics and cognitive psychology, possibly even law or business, I think it's important to know that there is many ideas about what a heuristic is, and you could even possibly develop your own idea, and this can give different insights than the traditional insight that a heuristic is something that people do because they cannot do otherwise, and this leads to worse decision, which, if you look at Herbert Simon's writings, you will probably strive to find him saying that. He said so many things. You may find something like that, but he definitely emphasized that heuristics are, in some sense, the only reasonable solution to making good decisions. But let's unpack a bit what we did. Let me formalize, so to say, a little bit of a claim. It's not very different from what I've been saying, so we can go through it maybe a little bit quickly. We are trying to contribute to the literature in cognitive psychology, operational research, which is in a way the core of analytics, as we all know, as well as machine learning, and try to say that not in the lab, not if you data fit or not if you choose the problems, but if you look at the representative ecology of problems, then possibly simplicity and transparency are not necessarily a trade-off with accuracy, and we have to understand when we can have our cake and eat it too, as they say, and when we cannot. Because now I cannot even look at the clock. Can somebody tell me how much more time we have so I don't eat from other speakers' time and from questions' time?
About another 15 minutes.
Okay.
Including questions. Including the questions.
That's including the questions. So I'll try to
Yeah.
be done in 10, so maybe even earlier. So we have a nice conversation that could be more useful. So as you see, last bullet of the slide, I have a few cases. You already saw one with the PIMA women, but I have some more salient ones. And then to tell you a little bit how we're building the mathematical theory. I was anyway not sure I would go into the mathematics, but I think I'll just outline it. So of course, this is the White House. And as you may be guessing, I'm going to be talking about the previous election. So Nate Silver, very successful in many occasions, unsuccessful here in terms of putting more than a 50% probability, considerably more for Hillary Clinton while Donald Trump won. So he was inaccurate. Of course, models cannot always be correct. We know that already from George Box. The idea is that whether they're useful. Silver is attempting to be useful and transparent in his website. So if you click through various links, you will find an explanation of how he came up with the 71% probability prediction. Again, I would ask you to think not like data scientists. I know it's hard for people like us, but we have to. If we're going to be reaching out to consumers and policymakers and other decision makers, we have to think like they think. So I'm not going to go through that, but basically what it kind of says is that his model is a regression on outputs of regressions, basically with corrections, with technical adjustments, trying to avoid overfitting, and so on and so forth. And I just don't think that clears the bar of being transparent to a normal, quote unquote, person. Another way is to do it based on a domain theory that includes psychology, sociology, economics, people, and framed in plain language that people can understand. So a political science professor from Washington, D.C., Alan Lichtman, has done that. He has come up with essentially a Turing rule. He has 13 keys, which are cues, features, and he has a Turing rule which says if 6 more of those are false, the challenger will win. They're all phrased so that they are true or false. Some of them are a matter of reality, a fact. For example, key number 3, the incumbent party candidate is the sitting president, either he is or she is or not. Others require some kind of judgment, as for example, no sustained social unrest during the term, blah, 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 and so on. Nevertheless, what Lichtman always does, he fixes those cues, he makes the judgment a few months before the election, and then he lets it go. In the case of Hillary versus Donald Trump, he had predicted Trump will win by finding that 6 of these keys were false. For the record, because that's probably coming as a question, he's now predicting, he has fixed his model now already, he's predicting Biden. Okay. On to a little more complicated situation where it's a little more clear. By the way, I think you've been seeing it, that as we're moving from the PIMA women to the election and to this example now, you can see that probabilities look more and more scarce to find, and this is really the case here. So this is something I worked on personally with a doctoral student, and what he did, he went to WikiLeaks at the time that it was still possible to get stuff from WikiLeaks. That was only for a week, and he was able to download 1,060 reports from NATO checkpoints in Afghanistan for 6 years. There are 7 successful, quote-unquote, suicide attacks. The big problem here is that many times civilians try to drive through these checkpoints, and what happens is they get nervous, they don't stop on time, or they think they could just go through, and then they're being shot eventually by the soldiers, resulting to injury or death. Everybody agrees, no matter if you're in the right or in the left part of the political spectrum, if you're not in the spectrum at all, if you're neutral, if you're an activist, if you're a military person or whoever you are, everybody agrees that these kinds of casualties are too many. So can we reduce them? This is the data that Nicholas, the student in Berlin, downloaded. This is the way report looks. There's access here for sensitive information, but you see you can find cues, features, attributes from this kind of data. For example, this car had 2 local nationals. It failed to stop, so both of the people were wounded. So we know the cues and we know the outcome. So we can build models. The problem is, I said, that we don't have any hits. If by hit you mean that the soldiers were able to stop a suicide attack. And we have very few misses. So you cannot really build reliably any of the models like CART. You cannot build anything. And here comes another possible advantage of the simple heuristics, such as the fast and frugal trees we're developing. They can be induced statistically, just like CART. And in the project, we spell all these different rules out. This was, to the largest extent, the work by Osgood and Marcus to specify formally these rules and to test them and to pick the best ones and to show how they do compare to other rules for inducing trees, such as in CART, to also check how often CARTs are fast and frugal trees and so on and so forth. But beyond this statistical world, the fast and frugal trees are robust, let's say, to bad information, impoverished information in the wild, in the sense that can also be used by standard methods of human factors, such as cognitive analysis. I'm going to skip that in the interest of time. This simply, currently, soldiers don't have any formal, precise method, but just some vague instruction, and we provided, which is in plain English, and we provide again some instruction in plain English, but which is formal and can be replicated and tested in a simulation. So this is again a fast and frugal tree, 1 question, possibility of an exit, only 1 cue. And it was devised by sitting down with practitioners without them looking at the data, because that would be equivalent to data fitting, but simply inducing the tree non-statistically, which we're able to do, and it wasn't able to do for any other methods. Quickly, this is a very good cue. if there's more than one person in the vehicle, then almost certainly this doesn't include hostiles, suicide attackers. Everybody agreed with that, so we put that on the top of the tree. And then we went down with a few other intuitive cues mentioned in the interviews. And if had this been used, then we would have reduced civilian casualties by more than 60%. And in fact, because this never happened, this is just an estimate. And it is in a way an upper bound, because this 78 includes that everybody that was classified as suicide attacker was hurt. But in fact, in reality, soldiers were more subtle in applying force, so they were not hurting anyone that they thought was a suicide attacker. But anyway, finally, my last case, and I want to flag that as well, because in the previous example, for example, with the PIMA women for the diabetes, we engaged in normal cross-validation out of sample. Here we're engaging in out-of-population measurement, in the sense that really here in this case where the idea was to predict cancer survival times for people, all models were trained in one population, literally in one country, but they were tested on other countries. So if you look at this paper in bioinformatics, there were 7 or 8 countries, I think, and you were always testing on countries that the model had not seen. So this is a tough, real out-of-population test. And as you can see here in the parentheses, you have confidence intervals. These are, again, balanced errors. If you quickly scan it, you will see that basically tallying, this very, very simple thing of just getting the cues and adding them, but just only estimating their cue direction, the future direction, you do as well as good benchmarks in regularized regression, such as Ridge and Lasso. Okay. I had forgotten that I have the simple, an even more striking case, but I think you may have seen that, and we also have a journal article coming out. I'm just going to skip through it very quickly. It really has to do with the Google flu trends. By many people, it has been beaten to death. I'm skipping now. Sorry about that, but I want to tell you a little bit about the theory. It's also in the book and a journal article. Quickly, if you look at only that, you see, if you're trying to predict the flu, the Google flu trends, the red curve, is very bad. And if you simply do either a two parameter linear regression on the most recent observation, or only use that observation without using a regression, which is called naive forecasting, and here's the blue line, the heuristic, you do much, much better actually. So we thought that was striking and surprising, and building on the results by Leisure et al. in a very strong way. Okay, we also have, of course, meta-analysis is in the book. We have not just this, we're not cherry picking. Here you can see a little bit of the larger picture. It's not very different if you use something like random forest, but we're picking the transparent AI method card. And you can basically see that, in fact, here there is a slight advantage to CART on the average, but not for every data set. Each point here refers to a data set. And clearly there's a big advantage for tallying and fast and frugal tree in terms of transparency. Okay, luckily I don't think I need to spend too much on that. The bias variance decomposition in this crowd, I'm sure a lot of people know it. Of course, strictly speaking, the bias variance decomposition applies to a regression problem, not to a classification problem as we have here. But the story has been unfolding in terms of the regression problem and the theory. You know that the prediction error is basically a trade-off between bias and variance. And the idea often is that simple models, of course, have more bias, but they have more variance. What we have been having, this is a high-level summary of the analytical results, is that, of course, it's well known about the statistics that bad information, no probabilities, information in the wild can lead to lower variance, but also structural reasons can lead to simple heuristics such as lexicographic heuristics, as fast and frugal trees or tallying, in fact, having sometimes optimal bias, or at least bias equal to standard linear models. Dominance is a of conditions that leads to that. There's been good papers published on that. I'm not going to go to that in case someone really wants to. I want you to see that it is here. Under a quite wide range of dominance conditions, which are not impressive. This is also Osgur's work at NIPS, which are not rare in the real world, these kinds of dominance conditions. In fact, you can get the simple heuristics to, in fact, have optimal bias. So that was also something people didn't really expect and gives a theoretical background. It's not simply getting lucky and finding that transparent models are quite accurate. Okay, let me wrap up. Since of time, this is coming up, as I said, and I will leave you with this on the screen, which is the claim. The claim was that we set out to flesh out and formalize what Herbert Simon had been saying for decades. We tried to connect to models, not only concepts or verbal labels across psychology, OR, and machine learning. And basically, we wanted to understand a little bit better this purported trade-off between transparency and accuracy. Leaders in interpretable AI, such as Cynthia Rudin, have also been vocal in saying that this need not be. And, we're trying to contribute that. And I think as Dart is making an entry into solving difficult problems in an innovative way, there's no question that IIT Madras has a excellent capacity into building the algorithms. I simply wanted to just try to plant the seed, as Nandan and knows from his various visits to the Max Planck and my visit at MIT, that it's possible to perhaps build some algorithms by having one leg onto human psychology, and perhaps make them at the same time as accurate as before, perhaps even more sometimes, and transparent. So thank you for listening. I'm sorry you cannot see me. I'm open to questions now. We can also get rid of the slide and put back the video. I don't know what's the best way, so we can have a nice conversation now.
Yeah, I think you can try starting your video now. So hopefully,
okay. Should I sharing, right? That would probably be better.
Sure. Yeah.
Yeah.
So
okay.
Folks, field is open for questions.
All right. Good.
So, Ravi,
I have a question. I'm Rahul.
Yeah. Hi. Go on.
The heuristics that you were highlighting in the claim, are you talking about domain-specific heuristics or in general domain-agnostic heuristics?
That's an excellent question. Of course, to the extent that we get inspiration by behavior, in every domain, the heuristic may look a little bit different. So, for example, the one that you saw about the checkpoints with, of course, in which you will have the exact same thing. But the formal aspects, they're domain in general. We emphasize that. In that sense, we're at the same footing and level of rigor with any other data science or our economics approach, which tries to build general models. It's simply that the structures we emphasize, I didn't go through that, but if we look at the tree structure, for example, it's always a lexicographic tree structure, right? With this exit at its level. For the linear model, we'll simply look at unweighted combinations. So they're both domain specific and domain general in these two senses.
Okay, thank you.
Yeah, Raj.
Roger.
Kostas, thank you very much for a very insightful talk. I had a question regarding what one can assume in terms of the expertise level of the user. So the analogy I have in mind is Atul Katwandi and others have written about checklists, and they say that when you're trying to design a checklist, you make something very simple if it is really for the expert, because you just need to jog his memory. Whereas if it is meant for a novice, then a very detailed one. Is there something along those lines that one needs to take care of when designing?
this is also, I think, this would be very important for building some good application that American Express or your other sponsors or whoever you're working with will be happy. So of course, in what we do with the checkpoints, the experts are the users, the soldiers. You can have it a little more complicated, if you will. It's not going to go to the public domain. If you're talking now about these other kinds of applications that lately have caught the public eye, such as being rejected for a loan, being tried while you're awaiting bail, where the demands of transparency are and should be enormous, of course, you have to put the bar much lower. Here, what I would say, there's a sense in which for many decisions that we're all making, we're all experts, right? And we all know a lot. So if I'm going to use if I'm going to pick up an apartment or a car, I've done this or I've done similar things before. So I don't think it would be wrong or a big burden to ask any regular consumer to sit down with you and make some trees and then test those and so on and so forth. It's again, as with Rahul's question, this has two components. It has a component of domain specificity, and it has a component of domain generality. Of course, sometimes I think our approach will fail, as all approaches fail. The question always is in building the toolbox and knowing when to go the information-hungry way and when you can afford not to. Yeah. And I guess my message, our message, because this is really, I'm really just a messenger of a research group that's growing and growing, has been working for decades and in different universities. The idea is to really try to understand when to do one and when to do the other and not assume. Many people are assuming, oh, if you make it simpler, it's going to be worse. Maybe you want to make it simpler because you have to, because people have to understand why they didn't get a loan, but it will be less accurate. I think, if we are scientists, we simply have to test this empirically. It's not just because it looks like it. It has to be, or that it is like that in all cases.
Great.
So this is really interesting for us also. One of my PhD students has been doing some work in this direction. Essentially, we want to learn simple models, right? And what we do is we change the data distribution so that the model fits better to the new distribution. But the question is it should perform better on the test distribution. So the different from the test. And we're able to get much better performance. Sometimes even like 150% improvement on the test data. I'll send you some of those papers.
Yeah, I would like to see that. I think actually these ideas are in many different places. Simply, I think still the balance of opinion, which also influences research, is in saying if you make it too simple, it cannot be good. It's a similar balance of opinion that's to some extent unfounded, exists in the behavioral science. If you let people decide, they will be bad, But this is really not always true. There's still things in which machine algorithms cannot make as good decisions. Maybe one day everything will be automated. I don't have a problem with that, as Greg was saying yesterday. But we shouldn't think we're in that place if we're not yet. That's all, right? And we should get in that place with measured steps and knowing what we're doing before automating everything.
I completely agree.
Yeah.
So
Thank you very much, guys. Very nice to see all of you. I'll switch my video, but I'll stay around, of course.
Thank you.
Thank you.
And I'm dropping off.
Okay. Thanks, Avi, for chairing the session.